In the last episode, we built a voice agent that runs in the browser. Sub 200 millisecond latency, ElevenLabs bidirectional WebSocket, streaming cascade. It works, it's impressive in demo. And the client says, great, can it work on a real phone call? The answer is yes. But the path from a browser demo to PSTN phone call is not a configuration change. It's an architecture change. The audio codec is different. The network transport is different. The echo characteristics are different. And if you do not handle all three, your agent either cannot understand the caller, talks over itself, or drops the connection silently. In this episode, we are going to build a telephony bridge using Twilio, the most common path for getting a voice agent onto a real phone number, and we are going to look at two fundamentally different approaches. The raw media streams proxy, where you build and own the entire audio pipeline, and ConversationRelay, where Twilio manages the pipeline and you focus on the logic. By the end of this episode, you will know which one to use and why, and you will have the code for both. This is the episode 2 of the Voice AI Engineering series. Let us get into it. Let me start by showing exactly what changes when you move from a browser WebSocket to a PSTN phone call. When your voice agent runs in the browser, you control the full audio pipeline. You capture audio with the browser's media encoder API at 16 kHz. You transmit it over a clean WebSocket connection that you own. You receive audio back and play it through the browser's audio context. On the PSTN, the public switch telephone network, meaning real phone calls, none of that is true. First, the codec. PSTN standard audio codec is MULO PCMU at 8 kHz, not 16. Not 44, 8. MULO is a logarithmic encoding designed in the 60s for telephone networks. Your ElevenLabs audio, which is 22 kHz linear PCM, cannot be sent directly to the PSTN. You have to transcode. The second is the transport. Twilio delivers the PSTN audio to your server using its own WebSocket protocol, Media Streams. The audio arrives at base 64 encoded MU low frames, packaged into a specific JSON envelope. You decode those frames, convert them to the format of your STT service expects, process them, and re-encode your TTS output back to MULO for the return path. Third, echo. On a phone call, the caller speaker output leaks back into their microphone. Your agent hears its own voice, transcribes it, and tries to respond to itself. Without acoustic echo cancellation, the agent enters a feedback loop and the call is broken within seconds. These three differences, codec, transport, and echo, are what this episode addresses. Let me show the two architectural paths for handling a Twilio phone call. When you receive a phone call through Twilio, you have two ways to handle the audio. The first is Twilio Media Streams. In this mode, Twilio acts as a raw audio delay. It takes the MULO audio from the phone call and streams it to your server over a WebSocket connection. Your server receives raw audio frames, processes them however you like, transcription, LLM, TTS, and sends audio back to Twilio, which puts in back on the phone call. You own the entire pipeline. You control everything. You also handle everything: codec conversion, echo cancellation, buffer management, reconnect logic. The second is ConversationRelay. This is Twilio's managed real-time voice API. You tell Twilio, here is a WebSocket endpoint, connect the caller to it. Twilio handles the codec conversation, the telephony signaling, and the turn-taking protocol. Your server receives transcription events and sends text responses. The TTS synthesis is handled by a provider you configure, which can be ElevenLabs. You get much simpler integration surface. You give up fine-grained control. The code we are building today supports both modes for a single server. A feature flag switches between them. Use relay equals true, sends incoming calls through the conversation relay, and use relay equals false, routes them through the raw media streams proxy. Both branches connect to the same ElevenLabs checkpoint and endpoint and the same LLM. Only the audio handling layer changes. Let us start with the harder part, the raw media streams proxy. When a call comes through Twilio calls the TVIML webhook on your FastAPI server. You respond with a TVIML instruction that tells Twilio to connect the audio to your media stream WebSocket endpoint. From that point on, Twilio is your audio source. Every 20 milliseconds, it sends a WebSocket message containing base 64 encoded MULO and audio frame. The JSON envelope looks like this. Event type is media. The payload field contains base 64 string, and sequence number tells you the frame order. Your server decodes the base 64 string giving you a bytes object of raw mu-low audio. That is a 160 byte chunk of 8 kHz audio. 20 milliseconds of a phone conversation. The first thing you need to do is convert that to a format your speech-to-text service can handle. Most modern STT services expect linear PCM at 16 kHz. So you need two steps. Mu-low decode, then upsample from 8 kHz to 16 kHz. Mu-low decoding converts the logarithmic encoding back to linear amplitude values. Python's audio OOP module has a uload to lin function that does this. Upsampling from 8 kHz to 16 kHz is a simple linear interpolation. For every input sample, you produce two output samples. On the return path, after your TTS engine produces 22 kHz linear PCM audio, you need to do downsample to 8 kHz and then mu-low encode it before sending it back to Twilio. Let's go back to the VS Code and check the media stream PY from the episode 2 telephony bridge. Look, media payload is getting payload from the media, and ULO is base 64 decodation of this media payload, and another conversation from the ULO to PCM 16. At the PCM level, we are cancelling the echo. The cleaned is here, and it's converted to back downsample. I mean, this is the upsample and this is the downsample to the encoded variable. Then we return the base 64 encoded of this downsampled audio. Now let me show the mu-low codec in detail, because getting this wrong is the most common reason voice proxies silently fail. Mu-low is a compounding codec. Compounding means compress and expand. You compress the dynamic range during encoding and expanding during decoding. The goal was to maximize voice quality over limited bandwidth like telephone lines. At 8 kHz, a 16-bit mu-low sample takes 8 bits, half the space of linear PCM. There are two things that break developer implementations consistently. The first is the byte order. The mu-low PCMU frames from the Twilio are big endian. Python's audio ulow to lin function expects the input as a bytes object and the output with S2, meaning 16-bit output samples. If you pass the wrong width, you get garbage. Numerically valid output that sounds like white noise. The second is the sample rate chain. You have three sample rates in the system: 8 kHz from Twilio, 16 kHz from STT, and 22 kHz from ElevenLabs. Each transition requires explicit sampling. If you skip a step, for example, if you feed 8 kHz audio directly to STT service configured for 16 kHz, the transcription will work, but everything will sound like it's in slow motion, like this. The STT model interprets the lower sample rate as a slow speaker, and the work boundaries shift. The mu-low PY module in this episode's repo handles all three transitions explicitly. Decode mu-low converts Twilio frames to 16 kHz PCM. Encode mu-low converts TTS output back to 8 kHz mu-low. Upsample and downsample handle the resampling using Python's audio rate CV function, which gives you clean sample rate conversion without an external dependency. Let's go to the Visual Studio VS Code. At the mu-low PY, we can see decode and encode mu-low functions and upsampling and downsampling here cleanly. Now let me show the third piece of the media streams proxy: acoustic echo cancellation. When your agent is speaking, the caller phone speaker is playing the audio. Some of that audio leaks back into the caller's microphone. Twilio picks it up and sends it back to your server. From your server's perspective, it looks like the caller is saying something, but they are saying is your agent's own voice, slightly delayed and degraded. If you do not cancel this echo, the agent transcribes its own speech, passes it to the LLM as a user utterance, and generates a response to its own words. The call sprawls into an incoherence within a few exchanges. Acoustic echo cancellation solves this by maintaining a reference signal, a copy of what the agent is currently saying, and subtracting it from the incoming audio before transcription. If the incoming audio matches the reference signal with high enough correlation, it is marked as an echo and discarded. In AAC PY, we implement a simplified AAC using a linear filter. We maintain a ring buffer of the most recent audio agent has been speaking. For each incoming mu-low frame, we decode it, correlate it against the reference buffer, And if the cross correlation exceeds a threshold, we suppress the frame. This is not broadcast quality EAC. For that, you would use WebRTC's EAC3 algorithm or dedicated library like Speaks DSP. But it is sufficient for conversational agents where the echo delay is predictable and speaker volume is relatively stable. The key parameter is suppression threshold. Too aggressive, and you will suppress the legitimate caller that overlaps the agent's output. Too conservative, and you will get the echo. I use 0.6 as default cross correlation threshold for phone quality audio. Here's the ICPY in the VS Code. I can show it to you. This function cancels the echo, and we are calling that from the media stream PY, the cancel echo function from the EAC, and it cancels the echo at line of 18, and we have a cleaned output. Alright, let's run the live demo call with this example. Let's go to the bridge and let's disable EAC and run our server at port 8022. Let's go to another terminal, and with ng-ronc, let's host it to my development ng-ronc domain, my localhost 8022. Let's check it in the browser. Is it running or not? Yep, method not allowed means it's required post. So we will connect this endpoint to do Twilio, and let's make a call. Alright, I need help with my order. Let's end the call and go back to our terminal. Let's enable EAC and run it again. Now it's running again with EAC enabled. Let's go back to Twilio and redeal. I need help with my order. Okay, let's go back our terminal. Let's stop the server and let's check the results. And let's summarize logs. Yes, as we can see, definitely we have EAC disabled inbound and EAC enabled inbounds and artifacts here. Now let us look the other architectural path, the conversation relay. Conversation relay is Twilio's answer the just I want to connect to an LLM phone call use case. Instead of streaming raw mu-low audio into your server, Twilio handles the STT itself. When the caller speaks, Twilio transcribes the audio and sends a transcription event to your WebSocket endpoint. When you have a response, you send a text message back. Twilio synthesizes it using a configured TTS provider, which can be ElevenLabs via the voice ID you specify in the TVI ML, and plays it to the caller. The WebSocket protocol is much simpler. Instead of binary audio frames every 20 milliseconds, you exchange JSON messages, transcription events inbound, text responses outbound. The TVML setups for conversation relay takes about 15 lines. You point the connect verb at a stream element with the relay URL. You configure the TTS provider and voice ID. That's it. No codec handling, no EAC, no buffer management. Twilio owns all that. What you give up is precision. You cannot inject your own EAC tuning. You cannot control the STT parameters, language, profanity filter, confidence threshold. You cannot buffer or manipulate the audio stream before transcription. If Twilio's managed pipeline makes a choice you disagree with, you cannot override it without switching the raw media streams path. For most production voice agent use cases, call centers, AI receptionist, appointment booking, conversation relay is the right choice. You get the reliable, low-maintenance integration in a fraction of the code. For specialized cases, real-time translation, multi-speaker scenarios, custom noise cancellations, this kind of thing, you want media streams. Let's check out the code, realizations PY. As you can see, that's all. The event loop receiving transcription events and sending text responses. Let's open the media stream PY in the site. Look how much longer it is. Realization is drastically shorter to build in code. There is one more conversation relay feature worth covering in detail: digital pauses and prefetching, which are what make the managed path feel as natural as the raw path. When your agent finishes a sentence and is waiting for the LLM to generate the next sentence, there is a silence gap. On a phone call, a half a second of silence sounds like drop connection. The caller starts talking, your agent starts talking, you have a collision. Conversation relay provides two mechanisms to handle this. The first, digital pauses. You can send a pause action to Twilio while your LLM is thinking. A short or let me check that, or simply a brief silence marker. This tells Twilio to play a brief sound, a thinking sound, a hold tone, or actual silence to signal the caller that the agent is still processing. This prevents the caller from assuming the line is dead. The second is prefetching. ConversationRelay supports injecting the first sentence of a response before the full LLM completion is available. While the LLM is generating sentences 2 through 5, Twilio is already synthesizing and playing sentence 1. This gives you streaming style latency within managed architecture without you building the streaming pipeline yourself. In Relay Session PY, prefetching is implemented by streaming the LLM response token by token, detecting the first sentence boundary and immediately sending that sentence to Twilio before the rest of the LLM completion arrives. This is the same sentence boundary detection from the episode 1. The same is sentence end function, but now deriving a conversation relay text response instead of an ElevenLabs flash signal. Go back to Relay Session PY. As you can see, there is a digital pause and interruption sensitivity here. Now that you have seen both paths in detail, let me give you a decision framework for choosing between them. Here's how I decide between media streams and conversation relay for a client project. Use conversation relay if your primary requirement is getting an LLM onto a phone call quickly and reliably. You need a call center automation, an AI receptionist, appointment booking, order status, standard conversational use cases. Your team does not have bandwidth to maintain a custom audio pipeline. You want Twilio to handle STT, codec conversation, and echo cancellation. Conversation relay is your choice. You will have a working demo in an afternoon. Use media streams if you need precise control over the audio pipeline. Examples: you are doing real-time translation where you need access to raw audio for language detection. You have a noisy environment where Twilio's built-in STT accuracy is not meeting your needs, and you want to switch to deep ground or assembly AI. You need multi-speaker diarization, identifying which person on call is speaking. You need to record and analyze the audio independently of the transcription. In any of these cases, conversation relays abstraction is working against you. Sorry about that. You want media streams now. The dual mode architecture is in this episode's repository. Lets you start with conversational relay. Ship fast, validate the use case, and switch to media streams when specialized requirements emerge. You flip one flag. The core LLM logic and ElevenLabs integration do not change. Let me close with the key patterns to carry forward. 4 things to take from this episode. 1. The PSTN is not the browser. MULO 8 kHz, Twilio's WebSocket protocol, and echo feedback are 3 differences that break native browser to front forks. Know each one before you start. 2. MULO decode and encode must be explicit. Every sample rate translation in your pipeline, 18 to 16 kHz for STT, 22 to 8 kHz from the TTS back to Twilio, must be an explicit resampling step. Silent mismatching produces audio that sounds valid but slightly wrong. 3. Start with conversation relay. It handles the codec, the echo, and the turn taking. Switch to media streams only when a concrete requirement forces you, not because you want more control in abstract. 4. Digital pauses and prefetching are what make managed pipelines feel natural. They are the difference between an agent sounds like a phone tree and one that sounds like a person thinking. The full code is in the Voice Agent Architect Lab repository at the branch episode 2. Link is in the description. In this episode 3, we are going to do something completely different. We are going to use OpenAI Vision to identify an entity from an image and generate a brand new, unique voice for that entity using ElevenLabs voice design IP. In real time, on the fly. Multiple entities, multiple voices, all switching within a single agent session. If you want to see you there, please subscribe and hit the like button, please.